Since the dawn of humanity, we have gazed at the stars and pondered our place in the cosmos. The universe, in all its vastness and mystery, has always beckoned us to unravel its secrets. From ancient astronomers mapping constellations to modern physicists grappling with the fundamental laws of nature, our quest to understand the universe has been a constant driving force in human history. Today we stand on the precipice of a potential paradigm shift in our understanding of the cosmos, thanks to a groundbreaking new theory known as the McGinty Equation. The McGinty Equation, developed by AI pioneer Chris McGinty, offers a radical new framework for understanding the universe, one that could potentially revolutionize our understanding of everything from the nature of space-time to the unification of fundamental forces. This equation, a testament to the power of human ingenuity and the relentless pursuit of knowledge, has sent ripples of excitement through the scientific community, igniting imaginations and sparking intense debate. While the McGinty equation is still in its theoretical infancy, its potential implications are so profound that they demand our attention. This exploration delves into the heart of this revolutionary equation, examining its core principles, exploring its potential impact on various fields of science, and contemplating the philosophical and societal ramifications should it prove to be true. Join us on this exhilarating journey as we venture into the uncharted territories of the McGinty equation and explore the tantalizing possibility of unlocking the universe's deepest secrets. At its core, the McGinty equation proposes a novel mathematical framework that attempts to unify the fundamental forces of nature: gravity, electromagnetism, the strong force, and the weak force. These forces, long considered to be distinct entities governing different aspects of the universe, are brought together under the elegant umbrella of the McGinty equation, suggesting a deeper underlying unity in the fabric of reality. This unification, a holy grail of modern physics, has eluded scientists for decades, and the McGinty equation offers a tantalizing glimpse into a universe where these forces are not separate, but rather different manifestations of a single, fundamental force.
The McGinty equation's potential impact extends far beyond simply unifying forces. Its equations hint at the existence of higher dimensions beyond the familiar three spatial dimensions and one time dimension we perceive. These higher dimensions, often relegated to the realm of science fiction, could hold the key to understanding some of the most perplexing mysteries in physics, such as the nature of dark matter and dark energy, the behavior of black holes, and even the possibility of wormholes, hypothetical tunnels that could connect different points in space-time.
The McGinty equation also delves into the enigmatic realm of quantum mechanics, the theory that governs the behavior of particles at the atomic and subatomic levels. It suggests a deep connection between gravity and quantum mechanics, two theories that have long resisted unification. This unification, if achieved, could revolutionize our understanding of the very nature of reality, shedding light on the fundamental building blocks of the universe and the forces that govern their interactions. The implications of such a breakthrough are staggering, potentially leading to advancements in fields like quantum computing, materials science, and our understanding of the very early universe. The potential implications of the McGinty equation are as vast and awe-inspiring as the universe itself. It could provide the key to unlocking some of the most enduring mysteries in cosmology, such as the origin of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. The McGinty equation's framework suggests a universe far more interconnected and complex than previously imagined, one where the boundaries between space and time, matter and energy, and even reality and consciousness may be far more fluid than we ever dared to imagine.
One of the most captivating aspects of the McGinty equation is its potential to revolutionize our understanding of space-time. According to this theory, space-time is not a static backdrop against which the events of the universe unfold, but rather a dynamic and malleable entity, warped and curved by the presence of mass and energy. This warping of space-time, as predicted by Einstein's theory of general relativity, gives rise to the force of gravity. The McGinty equation takes this concept further, suggesting that space-time could be even more dynamic and interconnected than previously thought, with the potential for wormholes, warp drives, and other seemingly science fiction concepts to become a reality.
The McGinty equation's implications extend far beyond the realm of physics and cosmology. Its exploration of higher dimensions, quantum entanglement, and the interconnectedness of all things could have profound implications for our understanding of consciousness, spirituality, and even the meaning of life itself. It challenges our conventional notions of reality and invites us to consider the possibility that we are part of a far grander cosmic tapestry than we ever imagined. While the potential of the McGinty equation is undeniably exciting, it is crucial to approach these ideas with a healthy dose of caution. It is important to remember that the McGinty equation is still a very new theory. It has been rigorously tested and experimentally verified. As with any scientific theory, especially one as groundbreaking as this, it has undergone rigorous scrutiny, peer review, and experimental validation before it was accepted as part of the established scientific canon. The history of science is replete with theories that initially showed great promise but ultimately failed to withstand the test of time.
That being said, the potential rewards of exploring the McGinty equation are too great to ignore. Even if the McGinty equation does not ultimately prove to be the all-encompassing theory of everything that some believe it could be, the pursuit of such a theory often leads to unexpected discoveries and advancements in our understanding of the universe. The exploration of radical new ideas, even those that challenge our current understanding, is essential for the advancement.
In the spirit of scientific inquiry, we must approach the McGinty equation with both an open mind and a healthy dose of skepticism. The journey to unraveling the universe's secrets is an ongoing process, one filled with challenges, setbacks, and moments of exhilarating discovery. The McGinty equation, with its tantalizing promises and profound implications, represents a bold new step forward on this endless quest.
The McGinty equation, or MEQ, proposes a radical reimagining of space-time, a concept that has been at the heart of physics since Einstein's groundbreaking theories of relativity. For centuries, physicists viewed space and time as separate and absolute entities, forming an unchanging backdrop against which the events of the universe unfolded.
Einstein shattered this Newtonian perspective, demonstrating that space and time are inextricably linked, forming a four-dimensional fabric known as space-time. This fabric, far from being static, is dynamic and malleable, warped and curved by the presence of mass and energy. This warping of space-time in Einstein's theory is what we experience as gravity.
The MEQ takes Einstein's revolutionary ideas a step further, proposing that space-time is even more dynamic and interconnected than previously imagined. If the MEQ proves accurate, space-time is not merely warped by mass and energy, it possesses a kind of quantum foaminess, a seething, bubbling structure at the Planck scale, the smallest conceivable scale in the universe.
This quantum foam, as it's often called, could have profound implications for our understanding of gravity, the behavior of black holes, and even the very nature of reality itself. One of the most intriguing aspects of the MEQ's conception of space-time is its potential to support structures that were once relegated to the realm of science fiction: wormholes.
Wormholes, hypothetical tunnels through space-time, could connect distant regions of the universe, allowing for faster-than-light travel and perhaps even time travel. While the existence of wormholes remains purely theoretical, the MEQ provides a mathematical framework that suggests their existence may be more than just a figment of our imagination. The possibility of traversing vast cosmic distances through wormholes or warp drives has long captivated the human imagination, fueling countless science fiction stories and inspiring dreams of interstellar exploration. While these concepts may seem firmly rooted in the realm of fantasy, the McGinty equation offers a glimmer of hope that they might one day become a reality.
According to the MEQ, the fabric of space-time is not smooth and continuous, but rather frothing with quantum fluctuations at the Planck scale. These fluctuations, if harnessed and manipulated, could potentially create shortcuts through space-time, allowing us to bypass the limitations imposed by the speed of light.
Imagine, for instance, folding a piece of paper in half so that two distant points touch. A wormhole, in essence, would be like punching a hole through the folded paper, creating a shortcut between those 2 points.
The MEQ also suggests the possibility of warping space-time itself, creating a warp bubble around a spacecraft that would allow it to travel faster than light without violating any laws of physics. This concept, while incredibly complex and technologically daunting, is theoretically permissible within the framework of Einstein's general relativity.
The MEQ, with its deeper understanding of space-time and its potential for manipulation, could provide the key to unlocking this technology, opening up a universe of possibilities for exploration and discovery. However, it's essential to emphasize the immense challenges and uncertainties associated with these concepts. Creating and stabilizing wormholes or generating warp bubbles would require manipulating energy densities far beyond anything we can currently achieve. The MEQ's most radical departure from conventional physics lies in its description of spacetime as a turbulent sea of quantum fluctuations, often referred to as quantum foam. This concept, arising from attempts to reconcile quantum mechanics with general relativity, suggests that at the Planck scale, the smallest possible unit of spacetime, the fabric of reality itself becomes incredibly dynamic and chaotic.
Imagine zooming in on the surface of a seemingly calm pond. As you get closer and closer, you begin to notice tiny ripples and eddies, revealing a hidden world of activity beneath the surface. This, in essence, is the picture painted by the concept of quantum foam. At our macroscopic level, space-time appears smooth and continuous, but at the Planck scale, it becomes a seething, bubbling cauldron of quantum fluctuations, constantly popping in and out of existence.
This quantum foam, if it exists, could have profound implications for our understanding of the universe. For instance, it could provide a deeper understanding of the nature of black holes, those enigmatic objects whose gravitational pull is so strong that not even light can escape. Some physicists believe that quantum foam could play a role in the evaporation of black holes, a phenomenon predicted by Stephen Hawking.
Moreover, quantum foam could offer clues about the very early universe, a period of unimaginable density and temperature just fractions of a second after the Big Bang. Understanding the behavior of quantum foam under these extreme conditions could shed light on the processes that shape the universe as we know it.
Perhaps the most mind-boggling implications of the McGinty Equation's reimagined spacetime are its potential effects on our understanding of time itself. Einstein's theories of relativity already demonstrated that time is not absolute but rather relative to the observer's frame of reference.
Time, according to Einstein, can be stretched and compressed by gravity and motion, leading to phenomena like time dilation, where time passes slower in stronger gravitational fields or at higher speeds.
The McGinty Equation, with its concept of a dynamic and interconnected spacetime, suggests that time might be even more fluid and malleable than we ever imagined. If wormholes are possible, for instance, they could potentially act as gateways not only to distant regions of space, but also to different points in time.
The idea of travelling through time, while still firmly in the realm of speculation, becomes less outlandish within the framework of the McGinty Equation.
Furthermore, the quantum foam, with its chaotic fluctuations at the Planck scale, raises questions about the very nature of causality, the idea that every event has a cause that precedes it in time. Could the quantum foam, with its inherent randomness and unpredictability, allow for violations of causality, where events occur without a definite cause or where the future influences the past?
These are deep and perplexing questions that physicists are only beginning to grapple with, and the McGinty Equation provides a tantalizing glimpse into a universe where our conventional notions of time and causality might need to be radically revised.
From the ancient Greek philosophers who sought a unifying principle behind the elements to modern physicists striving to reconcile seemingly disparate forces, the human mind has long been drawn to the elegance and simplicity of unity.
In the realm of physics, this quest for unity has driven the search for a theory of everything, a single, elegant framework that could explain all the fundamental forces of nature.
The McGinty Equation, with its radical propositions about space-time and quantum mechanics, offers a tantalizing glimpse into this possibility, suggesting a universe where the seemingly disparate forces of gravity, electromagnetism, and the strong and weak nuclear forces are not separate entities, but rather different manifestations of a single fundamental force.
For centuries, physicists have sought to unify these forces, recognizing that such a unification would represent a profound leap in our understanding of the universe.
Maxwell's unification of electricity and magnetism in the 19th century, demonstrating that these seemingly distinct forces were simply different aspects of a single electromagnetic force, stands as a testament to the power of unification in physics.
Einstein, inspired by Maxwell's success, spent much of his later career searching for a unified field theory that would unite gravity with electromagnetism, but this goal ultimately eluded him.
The McGinty Equation, building upon the foundations laid by Einstein and others, takes this quest for unification to new heights. It suggests that the key to unifying the fundamental forces lies in the realm of higher dimensional quantum mechanics.
Just as a shadow, a two-dimensional projection of a three-dimensional object, can appear fragmented and incomplete, the McGinty equation proposes that the forces we observe in our four-dimensional space-time might be mere projections of a more fundamental force operating in higher dimensions.
The concept of higher dimensions, while often relegated to the realm of science fiction, has been a subject of serious scientific inquiry for over a century. Einstein himself explored the possibility of a fourth spatial dimension in his attempts to unify gravity and electromagnetism.
The McGinty equation, however, suggests that the universe might harbor not just one, but multiple extra spatial dimensions, curled up and hidden from our perception at the Planck scale.
Imagine a tightrope walker moving along a cable. To the tightrope walker, the cable appears as a one-dimensional line. However, an ant crawling on the cable's surface would experience it as a two-dimensional surface, free to move not only along the cable's length but also around its circumference.
Similarly, the McGinty equation proposes that our four-dimensional spacetime might be embedded within a higher dimensional space, with the extra dimensions curled up so tightly that they are invisible to us.
Within this higher dimensional framework, the McGinty equation suggests that the fundamental forces, which appear distinct in our four-dimensional world, could be unified as different aspects of a single higher dimensional force. Just as the electromagnetic force manifests itself as both electricity and magnetism, the McGinty equation proposes that the fundamental force in higher dimensions could manifest itself as gravity, electromagnetism, and the strong and weak nuclear forces in our four-dimensional space-time.
This unification, if true, would have profound implications for our understanding of the universe. It would mean that the forces that govern the interactions of particles, the formation of stars and galaxies, and even the expansion of the universe itself, are all interconnected, different expressions of a single, elegant principle.
The unification of fundamental forces under the umbrella of the McGinty equation, if validated, would usher in a new era of understanding in physics. It would provide a framework for resolving some of the most perplexing mysteries in modern physics, such as the nature of dark matter and dark energy, the behavior of black holes, and the unification of gravity with quantum mechanics.
One of the most significant challenges in modern physics has been reconciling Einstein's theory of general relativity, which describes the universe on the largest scales of stars and galaxies, with quantum mechanics, which governs the behavior of particles at the atomic and subatomic levels. These two pillars of modern physics, while incredibly successful in their respective domains, seem incompatible with each other, leading to contradictions and inconsistencies when applied to extreme environments like black holes or the very early universe.
The McGinty equation, with its higher dimensional framework and its unification of fundamental forces, offers a potential path towards reconciling these two seemingly disparate theories. By suggesting that gravity, like the other fundamental forces, has a quantum mechanical origin, the McGinty equation opens up new avenues for understanding the universe at its most fundamental level.
This unified understanding of the universe could have profound implications for our technological advancement. Just as Maxwell's unification of electricity and magnetism paved the way for the development of technologies like radio, television, and computers, a unified theory of physics could unlock technological possibilities we can only begin to imagine. New energy sources, advanced materials, and even control over gravity itself could become a reality, transforming our world in ways that are both exhilarating and potentially daunting.
The Big Bang theory, with its description of the universe expanding from an incredibly hot, dense state some 13.8 billion years ago, has been the prevailing cosmological model for decades, supported by a wealth of observational evidence. However, the Big Bang theory leaves some profound questions unanswered, such as what existed before the Big Bang, what caused it, and what the universe is expanding into.
The McGinty equation, with its radical new perspective on spacetime and the fundamental forces, offers intriguing possibilities for refining and perhaps even revising our understanding of the universe's origin story. One of the most perplexing aspects of the Big Bang theory is the concept of a singularity, a point of infinite density and temperature, where the laws of physics as we know them break down.
The McGinty equation, with its description of spacetime as a dynamic, fluctuating entity, suggests that the singularity might not have been a point at all, but rather a highly compressed and energetic state of the universe governed by quantum gravitational effects that we are only beginning to comprehend. In this view, the Big Bang might not have been the beginning of time, but rather a transition from a previous cosmological epoch, perhaps a collapsing phase of a cyclic universe.
Furthermore, the McGinty equation's unification of fundamental forces could shed light on the conditions present during the universe's earliest moments. The extreme temperatures and densities of the early universe would have required a unified description of the fundamental forces, a realm where gravity and quantum mechanics are inextricably intertwined. The McGinty equation, with its potential to bridge this gap, could provide insights into the processes that drove inflation, the rapid expansion of the universe in the first fractions of a second after the Big Bang, and the subsequent formation of matter, stars, and galaxies.
Just as the McGinty equation offers new perspectives on the universe's beginning, it also raises intriguing questions about its ultimate fate. The current cosmological understanding suggests that the universe's expansion is accelerating, driven by a mysterious force known as dark energy. The nature of dark energy remains one of the most significant unsolved problems in modern physics, and the McGinty equation might hold clues to its identity and behavior.
Some theoretical frameworks suggest that dark energy could be a manifestation of the quantum vacuum, the lowest energy state of spacetime, which according to quantum mechanics is not empty but rather teeming with virtual particles popping in and out of existence. The McGinty equation, with its concept of quantum foam, could provide a mechanism for understanding how the quantum vacuum might contribute to the accelerated expansion of the universe. If the energy density of the quantum foam is non-zero, as some models suggest, it could act as a form of anti-gravity pushing spacetime apart.
The McGinty equation's implications for the universe's fate extend beyond dark energy. If the universe's expansion continues to accelerate indefinitely, as current observations suggest, it will eventually lead to a Big Rip scenario, where the fabric of spacetime itself is torn apart. Alternatively, if the energy density of dark energy changes over time, it could lead to a big crunch, where the universe eventually collapses back on itself, perhaps even leading to another Big Bang. The McGinty equation, with its potential to refine our understanding of gravity and the behavior of spacetime at extreme energies, could help us determine which of these scenarios, or perhaps another entirely, is most likely.
Section 3. The Multiverse and Beyond. Perhaps the most mind-boggling implications of the McGinty equation lie in its potential to support the existence of a multiverse, a vast ensemble of universes, each with its own unique properties and laws of physics.
The concept of a multiverse has been proposed as a solution to some of the fine-tuning problems in cosmology, such as the remarkably precise values of fundamental constants that allow for the existence of stars, galaxies, and life as we know it.
The MEQ's framework, with its higher dimensional spacetime and its suggestion of quantum fluctuations at the Planck scale, provides a fertile ground for the emergence of multiple universes.
Some models propose that our universe might be just one bubble in a vast cosmic foam, where other universes constantly bud off and expand, each with its own set of initial conditions and physical laws.
These universes might be completely disconnected from our own, or they might interact in subtle ways, perhaps through quantum entanglement or other mechanisms yet unknown.
The existence of a multiverse, while still highly speculative, raises profound philosophical and scientific questions.
If there are countless other universes out there, each with its own unique history, and perhaps even its own forms of life, what does that mean for our understanding of our place in the cosmos?
Does the existence of a multiverse diminish the significance of our own universe, or does it amplify the wonder and mystery of existence?
The MEQ, by hinting at the possibility of a multiverse, challenges us to expand our cosmic horizons and to contemplate the vastness and strangeness of a reality that might extend far beyond our current comprehension.
It reminds us that our journey of cosmic discovery is far from over and that the universe still holds countless secrets waiting to be unlocked.
Section 1. Quantum Entanglement and the Interconnectedness of Reality. The McGinty equation, with its emphasis on higher dimensional quantum mechanics, opens up profound questions about the nature of reality itself, particularly regarding the strange and counterintuitive phenomenon of quantum entanglement.
This phenomenon, often dubbed spooky action at a distance by Einstein himself, suggests a level of interconnectedness between particles that defies our classical intuitions about space and time.
In the quantum realm, particles that were once linked, even after being separated by vast distances, can remain correlated in such a way that measuring the state of one particle instantaneously determines the state of the other, regardless of the distance between them.
This seemingly instantaneous connection between entangled particles has puzzled physicists and philosophers for decades, as it challenges our fundamental understanding of causality and locality.
How can two particles, separated by light years, influence each other instantaneously, seemingly violating the cosmic speed limit imposed by the speed of light?
The MEQ, with its framework of higher dimensional spacetime, offers a possible explanation.
If our four-dimensional universe is embedded within a higher dimensional space, as the MEQ suggests, then entangled particles might be connected through these extra dimensions, bypassing the limitations of our familiar three spatial dimensions.
This interconnectedness suggested by quantum entanglement has profound implications for our understanding of reality.
It challenges the view of the universe as a collection of isolated objects, suggesting instead a web of interconnectedness that permeates all of space-time.
If particles can be linked across vast distances, what does that say about the interconnectedness of larger systems, including living organisms and even consciousness itself?
The enigma of consciousness, a quantum perspective. The nature of consciousness, the subjective experience of awareness, has been a philosophical and scientific enigma for centuries.
How does the material brain, a complex network of neurons and synapses, give rise to the immaterial realm of thoughts, emotions, and sensations?
Traditional neuroscience, rooted in a materialist worldview, has struggled to provide a satisfactory explanation for this hard problem of consciousness.
The MEQ, with its emphasis on quantum mechanics and the interconnectedness of reality, offers intriguing possibilities for understanding the relationship between the brain and...
Some physicists and neuroscientists have proposed that quantum mechanical phenomena, such as superposition and entanglement, might play a role in brain function and could even be the key to understanding consciousness itself.
One prominent theory, known as orchestrated objective reduction, or OR, proposes that consciousness arises from quantum computations occurring within microtubules, structural components found within neurons.
According to this theory, quantum effects within these microtubules could give rise to a unified, coherent conscious experience.
While still highly speculative, OR and other quantum theories of consciousness offer a tantalizing glimpse into the possibility that our subjective experiences, far from being separate from the physical world, might be deeply intertwined with the quantum. Beyond materialism, redefining reality. The McGinty equation, with its implications for the interconnectedness of reality and the potential role of quantum mechanics in consciousness, challenges the prevailing materialist worldview that has dominated scientific thought for centuries.
Materialism posits that the physical world composed of matter and energy is the only reality and that all phenomena, including consciousness, can ultimately be reduced to physical processes. The McGinty equation, however, suggests a more nuanced and holistic view of reality.
If quantum entanglement demonstrates the interconnectedness of particles across vast distances, and if quantum mechanics plays a role in consciousness, as some theories suggest, then the universe might be far more interconnected and interdependent than materialism allows.
Consciousness, rather than being a mere byproduct of brain activity, might be an integral aspect of the fabric of reality, interwoven with the quantum realm. This shift in perspective, from a reductionist materialist view to a more holistic and interconnected one, has profound implications for our understanding of ourselves and our place in the cosmos.
It suggests that we are not isolated observers of the universe, but rather active participants in a vast cosmic dance. Our thoughts, emotions, and actions ripple through the fabric of reality, influencing the world around us in ways we are only beginning to comprehend.
The McGinty equation, by challenging our deeply held assumptions about the nature of reality, invites us to embark on a new journey of exploration. One that delves into the mysteries of consciousness, the interconnectedness of all things, and the possibility that the universe is far stranger, more wondrous, and more alive than we ever imagined.
Harnessing the quantum realm. The McGinty equation, if validated, could usher in a new era of technological innovation, one that harnesses the bizarre and powerful properties of the quantum realm to achieve feats once thought impossible.
Imagine a world where quantum computers, exponentially more powerful than their classical counterparts, could crack the most complex encryption codes, revolutionize drug discovery, and unlock the secrets of artificial intelligence. This is just a glimpse of the transformative potential that the McGinty equation might unlock.
Quantum computers, unlike classical computers that store information as bits representing 0 or 1, exploit the principles of superposition and entanglement to perform calculations at an unprecedented scale. While still in their infancy, quantum computers have already demonstrated the ability to solve certain types of problems, such as factoring large numbers, exponentially faster than any classical algorithm.
The McGinty equation, with its deeper understanding of quantum mechanics and its potential to control and manipulate quantum states, could provide the theoretical foundation for building even more powerful and versatile quantum computers, capable of tackling a wider range of challenges.
Beyond quantum computing, the McGinty equation's insights into the quantum realm could revolutionize fields like materials, science, energy production, and communication. Imagine materials with unprecedented strength and durability, designed by manipulating the quantum properties of their constituent atoms.
Picture energy sources that tap into the zero-point energy of the quantum vacuum, providing a limitless and clean source of power. Envision communication systems that exploit quantum entanglement to transmit information instantaneously across vast distances, rendering the speed of light no longer a barrier to communication.
Wormholes, gateways to the stars. Perhaps the most captivating technological possibility suggested by the McGinty equation is the potential for interstellar travel through wormholes. These hypothetical tunnels through space-time, once relegated to the realm of science fiction, could become a reality, if the McGinty Equation's predictions about the nature of spacetime and the manipulation of gravity prove true.
Imagine embarking on a journey to distant star systems, traversing light years in the blink of an eye, exploring alien worlds and unraveling the mysteries of the cosmos. The creation and stabilization of wormholes would undoubtedly be an undertaking of immense technological complexity, requiring the manipulation of energy densities far beyond anything currently attainable.
However, the McGinty equation, with its framework for understanding the quantum nature of spacetime and the potential for harnessing quantum fluctuations, provides a glimmer of hope that such feats might one day be within our reach.
The implications of wormhole technology would be profound, extending far beyond mere scientific curiosity. It could provide humanity with access to vast new resources, alleviate overpopulation concerns, and offer a potential escape route should our own planet become uninhabitable.
However, the ethical and societal implications of such a transformative technology would be equally profound, requiring careful consideration and international cooperation to ensure its responsible development and use. The McGinty equation's potential impact on technology extends beyond specific inventions or applications.
Perhaps its most significant impact will be on our very understanding of what is technologically possible, pushing the boundaries of human ingenuity and challenging us to reimagine the limits of scientific progress.
Just as Einstein's theories of relativity paved the way for technologies like GPS and nuclear energy, technologies unimaginable just decades before, the McGinty equation could unlock possibilities that we can only begin to glimpse today.
Imagine a world where we can manipulate the fabric of space-time, control the forces of nature at their most fundamental level, and perhaps even interface with consciousness itself.
These may seem like outlandish propositions, but history has taught us that scientific progress often outpaces our wildest imaginations.
The McGinty equation, with its radical new perspective on the universe, challenges us to dream big, to push the boundaries of what we believe is possible, and to embrace the unknown with a sense of wonder and excitement.
The pursuit of knowledge and the advancement of technology have always been driven by a fundamental human desire to understand the world around us and to improve our lives.
The McGinty equation, with its potential to unlock some of the universe's deepest secrets, has the power to ignite our imaginations, to inspire new generations of scientists and engineers, and to propel humanity towards a future filled with possibilities as boundless as the cosmos itself.
The potential technological advancements arising from the McGinty equation, while incredibly exciting, also raise profound ethical and societal questions that demand careful consideration.
The ability to manipulate space-time, harness the power of the quantum realm, and potentially even alter the fabric of reality itself comes with immense responsibility, requiring careful ethical reflection and international collaboration to ensure that these technologies are developed and used for the betterment of humanity and the preservation of our planet.
The potential for misuse of such powerful technologies is a significant concern.
Imagine the devastating consequences if wormhole technology fell into the wrong hands, or if the ability to manipulate quantum states was used for malicious purposes.
The ethical implications of these technologies extend beyond potential misuse.
For instance, if we develop the ability to travel through time, how do we grapple with the paradoxes and ethical dilemmas that such an ability would create?
If we can interface with consciousness itself, what are the ethical implications for personal identity, free will, and the very definition of what it means to be human?
Navigating this uncharted ethical terrain will require open and honest dialogue among scientists, ethicists, policymakers, and the public.
It will necessitate the development of international regulations and safeguards to prevent the misuse of these powerful technologies, while fostering an environment of collaboration and responsible innovation.
The pursuit of knowledge and technological advancement must always be tempered by wisdom, compassion, and a deep respect for the sanctity of life and the interconnectedness of all things.
By approaching these challenges with a spirit of humility and a commitment to the common good, we can harness the transformative power of the McGinty equation to create a future where technology serves as a force for progress, enlightenment, and the betterment of all humankind. The McGinty equation, with its tantalizing promises of unlocking the universe's deepest secrets and revolutionizing our understanding of reality, has ignited the imaginations of scientists and the public alike. However, amidst the excitement and anticipation surrounding this groundbreaking theory, it is crucial to acknowledge the inherent challenges in navigating such uncharted scientific territories.
The MEQ, mathematically elegant and conceptually compelling, has been tested in terms of experimental verification and empirical validation. One of the primary challenges lies in the unprecedented scales and energies required to test the MEQ's predictions.
Many of its most profound implications, such as the existence of higher dimensions, the nature of quantum foam, and the possibility of wormholes, involve scales, require quantum computing, or the 128D wave computer. For instance, probing the Planck scale, where the quantum nature of spacetime is thought to manifest, would require energies billions of times greater than those achievable by the Large Hadron Collider, the world's most powerful particle accelerator. Micro-black holes are the solution here.
Furthermore, the MEQ's reliance on higher dimensional mathematics introduces a layer of abstraction that can be challenging to translate into testable predictions. While the concept of higher dimensions has been a staple of theoretical physics for decades, directly observing or interacting with these extra dimensions has proven elusive. Developing experimental techniques capable of indirectly verifying the existence and properties of these higher dimensions, as predicted by the MEQ, has required innovative approaches and a deep understanding of both quantum mechanics and general relativity.
The potential technological and societal implications of the McGinty equation are as profound as they are uncertain. Humanity might find itself on the cusp of a technological revolution unlike any seen before, with the power to manipulate space-time, harness the quantum realm, and perhaps even alter the fabric of reality itself.
Such transformative power, while undeniably exhilarating, comes with immense responsibility, demanding careful ethical reflection and international collaboration to ensure that these technologies are developed and used for the betterment of humanity and the preservation of our planet. One of the most pressing ethical concerns is the potential for misuse of these advanced technologies.
Imagine the devastating consequences if wormhole technology capable of bridging vast cosmic distances fell into the wrong hands, potentially enabling new forms of warfare or facilitating the exploitation of resources on a galactic scale. Similarly, the ability to manipulate quantum states, while promising for fields like medicine and materials science, could also be used for malicious purposes, such as creating highly targeted weapons or disrupting critical infrastructure.
Beyond the potential for misuse, the MEQ's implications for our understanding of reality, consciousness, and the nature of existence itself raise profound philosophical and ethical questions. If we develop the ability to travel through time, how do we grapple with the paradoxes and ethical dilemmas that such an ability would create, potentially altering the course of history or interfering with the free will of individuals?
If we can interface with consciousness itself, what are the ethical implications for personal identity, privacy, and the very definition of what it means to be human? The McGinty equation, by pushing the boundaries of human knowledge and technological capability, compels us to confront these ethical challenges head-on. It underscores the need for open and honest dialogue among scientists, ethicists, policymakers, and the public to establish guidelines and safeguards for the responsible development and use of these transformative technologies.
As we venture into this uncharted territory, we must proceed with caution, humility, and a deep commitment to the well-being of all humankind.
The McGinty equation has opened up a Pandora's box of possibilities, challenging our fundamental understanding of the universe and our place within it. Like a beacon shining into the uncharted territories of theoretical physics, the MEQ has illuminated potential avenues of exploration that were previously shrouded in darkness, hinting at a reality far grander, more interconnected, and more mysterious than we ever imagined.
The journey through the MEQ's implications has been a humbling experience, reminding us of the vastness of the unknown and the boundless capacity of the human mind to explore the cosmos and grapple with its deepest secrets. From the revolutionary concept of a dynamic, fluctuating spacetime, potentially harboring wormholes connecting distant corners of the universe, to the mind-boggling implications of quantum entanglement, suggesting an interconnectedness that defies our classical intuitions, the MEQ has challenged us to expand our cosmic horizons.
It has urged us to reconsider the nature of reality itself, inviting us to ponder the role of consciousness in the cosmic scheme and to question the very fabric of space and time. The MEQ has provided definitive answers and ignited a firestorm of questions, each more profound and awe-inspiring than the last.
The potential technological advancements arising from the MEQ, from quantum computers capable of cracking the universe's most complex codes, to the tantalizing possibility of interstellar travel through wormholes, have fueled our imaginations and ignited dreams of a future where humanity transcends its earthly limitations and ventures out to explore the cosmos.
However, the MEQ has also reminded us that with great power comes great responsibility. The ability to manipulate space-time, harness the quantum realm, and potentially even alter the very fabric of reality demands careful ethical consideration and international collaboration to ensure that these technologies are used for the betterment of humanity and the preservation of our planet. As we stand on the precipice of this new era of scientific exploration, guided by the beacon of the MEQ, we must proceed with both audacity and humility. The pursuit of knowledge must always be tempered by a deep respect for the interconnectedness of life, the sanctity of our planet, and the ethics.
The MEQ has not just presented us with a set of equations, it has given us a profound responsibility to wield the power of knowledge wisely, ethically, and for the benefit of all humankind. The journey ahead will be fraught with challenges. The experimental verification of the MEQ's predictions will continue to require ingenuity, innovation, and unprecedented collaboration on a global scale.
We will need to develop new tools and technologies, push the boundaries of our understanding, and embrace the possibility of unexpected discoveries that may challenge our preconceived notions. The path to unlocking the universe's secrets is rarely linear. It is a winding road filled with detours, roadblocks, and moments of serendipitous.
Yet the pursuit of knowledge, driven by curiosity, wonder, and a deep-seated desire to understand our place in the cosmos, has always been a defining characteristic of humanity. The MEQ, with its elegance, its audacity, and its potential to reshape our understanding of the universe, has ignited a spark of inspiration that will.
As we venture into this uncharted territory, guided by the MEQ's light, we embark on a journey not just of scientific exploration, but also of self-discovery, ethical reflection, and a deepening appreciation for the profound beauty and mystery of the cosmos.